London dispersion forces are forces that happen when there's a non-polar molecule. Electronegativity is like 4 with our fluorine. 4 subtract 4 is giving us a 0. So again, equal attraction for electrons. Our electrons are shared equally, but they're constantly moving, which creates a temporary shifts in electron density. So sometimes we end up with these electron clouds that get pushed back and forth. So sometimes the electron may be closer to this fluorine, which would make this one where we're partial positive. We've got these temporary dipoles. So dipole is just a charge that's, or like a shift in those electrons. So those temporary dipoles are formed when more electrons move over and smaller, like when those, temporary dipoles are formed. So larger when more electrons move over, smaller when electrons are leaving. Okay, so we're going to have more London dispersion or stronger London dispersion first, the more electrons that you have on there. Okay. You've got this partial charge that's happened. We've got a negative dipole, we've got a positive dipole, negative dipole, positive dipole, and so those electrons have shifted over. This positive is going to be connected to this negative. So in the next moment, they might shift the opposite way, and again, we still have that attraction or that London dispersion there. Okay, so again, those temporary dipoles are close to each other. A weak London dispersion force exists between opposite charges of those regions. So again, it's very, very, very weak. And so a dipole is happening when we've got two charges on those different sides. What I would suggest doing is writing down this dipole, or this dipole here, even if it's just a note on the top of your page. So London dispersion forces are weak forces. There's that temporary shift of electrons to make those electrons clouds. Produces the momentary dipole. Again, it's going to be induced. Okay, so it's not like it's temporary. It's not permanent. As in like a polar molecule, it's always there. So all particles are going to exhibit dispersion forces. So weak dispersion forces, so the smaller particles, there's going to be fewer electrons. Again, this is at the bottom of your page. A stronger dispersion force, so larger particles are going to have more electrons that are there. So if we're comparing them with fluorine, chlorine, bromine, and iodine, all of them are halogens, we would have less London dispersion with their fluorine, more London dispersion with their iodine. And that's occurring because there's more electrons that are present. So this is just an example of it. So fluorine, we've got smallest halogen molecule. There's the fewest electrons, very small temporary dipoles because of the minimal attraction. So as a result, it's going to be a gas. Again, very low density, and it's a very, very low melting point. So at negative 219 degrees Celsius, fluorine is going to be a gas. Right? If we start getting to our chlorine, again, it's a small molecule. It's still bigger than our fluorine. There's more electrons that are there. It's still temporary. It's a gas, but then our density, we've got a higher density. And if you look at our melting points down here, so our negative 219.67 in comparison to our negative 34 degrees Celsius, our chlorines are sticking together a little bit better. If we move on further to our bromine, again, a larger attraction, we've got, so it's going to be a liquid here. The melting point is negative 7.2 degrees Celsius. Again, our density is significantly higher, or that's because we're more electrons. It's a bigger molecule, and then we've got larger temporary dipoles that are forming. Okay, more electrons there, larger the dipole that can happen. And then with our iodine, we've got 106 electrons that would be present, largest temporary dipoles for all of the halogens, largest attraction, so it's going to be a solid. The melting point is 113.7 degrees Celsius, okay, with a density of 4.93. So again, just an example of how it formed. You don't need to know that, just more so to prove to you what's going on. So the intermolecular forces are going to determine the properties of materials. So this you've already heard multiple times already. So weak London dispersion force determines that it's going to have a low density, so particles aren't close together. It's going to have a low melting point. It's going to be easy to separate those particles. It's going to vaporize easy. Vaporize just means turn into a gas. It's going to have a low boiling point, and we're going to see that it's either a gas or a liquid. We're not going to see a